So in this example, we're going to use the first derivative test, and we're going to find the extrema for the function x cubed minus 3x squared minus 9x minus 1. So let's go ahead and take our first derivative here. Right, we've got f prime of x. We'll just take the derivative of each term. So we'll get 3x squared minus 6x minus 9. Right, you'll notice that each of these terms have a 3 in common that you can actually factor out. So let's go ahead and factor this. I'll take the 3 out. That's going to give us x squared minus 2x minus 3. Right, and this is still something that I can continue to factor. Let's go ahead and factor that trinomial into 2 sets of parentheses here. Factors of 3 that subtract to give us 2 will be 3 and 1. And put our x in each of those slots. Right, just make sure you get your signs correct here. We need a negative 2x in the middle, so x minus 3 and x plus 1 is going to be our derivative in factored. Right, and if we're using this first derivative test, we want to go ahead and take our derivative, right, set it equal to 0, and we're going to find the critical points. Right, so take our derivative, set it equal to 0. This will help us find critical points. All right, so I'm going to take that whole function, 3 times x minus 3 times x plus 1, and set this equal to 0. Right, that means that one of these factors has to be equal to 0. So x minus 3 has to equal 0, or x plus 1 has to equal 0. And we'll get two x values here. Right, x equals 3, or x equals negative 1. Right, so you've got these critical points. I'm going to put these on a snapshot of the x-axis, right? So here's my negative 1, here's my 3, right? And think of this as your x-axis. So what it's doing is dividing your x-axis, right, into 3 different intervals, right? So I have what I'm going to call interval A, interval B, and interval C, right? So interval A is going to be everything from negative infinity to negative 1, right? Interval B is going to be everything from negative 1 to 3, and interval C is going to be everything from 3 to positive infinity, right? And what we want to do is take a test value inside each of those intervals, right? We're going to go plug that value into our derivative, right? And when we're using this first derivative test, right, we want to know, well, is our first derivative something positive, right? Is it greater than 0? If it is, that's going to tell us that our function should be increasing on the interval. Or is that derivative something less than 0 or negative? If it's negative, right, then it should be decreasing on that interval, right? So let's go ahead and pick a test point. It doesn't matter what interval you pick to do first. I'm going to go ahead and pick interval B, and I'm going to pick x equals 0 because that's always a nice test value to work with initially, right? And keep in mind, you're plugging it into your derivative, right? So I'm plugging it into f prime of x. So I'm going to calculate f prime at 0, right? And I don't necessarily need to know what the actual value is, but I do need to know whether it's going to be positive or negative, right? So however you want to work with that, if you want to find the numerical value, you can. So I'm going to go plug it in here. I'll use the factored form. So this will be 3. I've got 0 minus 3 and 0 plus 1, right? So I'm plugging it into this function. I'm going to use the factored form here. So this will give me 3 times negative 3 times positive 1, right? Which is going to give me a negative 9. So when I calculate f prime at 0, right, I'll write it out down here. So I've got it all in here. even though I did my work above, right? This is going to give me -9, right? And that value is negative, right? Which means it's something less than 0. So my conclusion here is that my function should be decreasing on that interval, right? So my conclusion is that this will be a decreasing interval, right? And now we can go ahead and go back and do the exact same thing for the other two intervals that we have, right? So I'm going to go pick interval C as my next one, right? I'm going to pick a test point. So I'm going to use maybe x equals 4 as my test value for interval C. And we're plugging it into the derivative, right? So f prime at 4, this will give me 3 times 4 minus 3 times 4 plus 1. Right, this will be 3 times 1 times 5, which will give me 15. Right, I don't necessarily need to care about what the number is. The important part here is that it's positive, right, which means my function should be increasing on that interval. Right, now let's go ahead and go work with the negative numbers up here with interval A. So I'll pick a test value. I'll pick x equals -2. Right, be careful with your negatives. Make sure you're actually in that interval. All right, so f prime at -2 is going to give me 3 times -2 minus 3 and -2 plus 1, which will give me 3 times -5 times -1, which will come out to give me positive 15. Right, and the important part is that it's positive, that numerical value. So my conclusion here is that this interval should be increasing. Right, and so as you're kind of looking at the graph, right, the graph of our function is graphed in blue. Right, that's our f of x function. The dashed lines that you see in orange are just representing the boundaries of those intervals, right? We had critical points at x equals -1 and x equals 3. So that's what I'm using just to kind of break apart the graph into those intervals. And when we use that first derivative test, right, when we're looking at that interval from -infinity to -1, right, we came out with a positive number when we plugged our test value in, right? That means our graph should be increasing on that interval. And it is, right? If you look at this graph of the function here, I'll see if I can write on this, right? This is an increasing batch, right, from our graph. And it's going to keep increasing until it hits, right, the y value up there at -1, right? And then you saw that from -1 to 3, this is a decreasing portion, right, of our graph. So it should be going downhill on that interval. And then from 3 to positive infinity was our third interval. When we plugged our test point in, we got a positive number. And so that means that this section of our graph should be increasing. And it is, right? You see this portion of the line is going uphill as you look at it left to right. Right, so as you're kind of going through your work, make sure you are looking at the graph, make sure it matches up with what you see. If it doesn't, right, that's your clue that you have an error somewhere, right? Go back and see if you can find it. So since this question was asking us to find the local extrema, right, you're looking for max and mins. So think about what's happening on the graph, right? Anytime your function is changing from increasing to decreasing, right? That's going to occur at a max. So if I come back and if I keep annotating here on the graph itself, right, when this changes from increasing to decreasing up here, this should represent some type of max value, right? Which is why -1 was a critical point, right? The derivative changing from positive to negative, which is going to be what makes that a max. When your function goes from decreasing to increasing, right? So looking down here, this is going to represent some type of minimum on your graph, right? Think about that in terms of the derivative, right? Your derivative went from being something negative to something that was positive, right? So if you want to go back and mark up what you're seeing here on the graph with regard to your derivatives as well, you can, right? So whenever your function is increasing, that means your derivative has to be something positive. Right, so that's both of these intervals. Right, whenever your function was decreasing, that means your derivative was something negative. All right, so now let's go ahead and take a look at our second derivative test for this. All right, so let's take a look at the second derivative here. Right, we know we're going to use that same original function for f of x. I'm going to copy over our first derivative that we had, which was 3x squared minus 6x minus 9. Right? And we want to use the second derivative to determine where the intervals are concave up and where it's concave down. And then that's going to also allow us to list the points of inflection. Right, so let's go ahead and calculate the second derivative. This will give us 6x minus 6. Right, and we want to take a look at where our second derivative is equal to 0. So we're going to take 6x minus 6, set it equal to 0, solve it for x. Right, you can factor out the 6 if you want, or you can work with it in there. It's up to you. Right, so x minus 1 in this case should be equal to 0. If we add the 1 to both sides, right, we're going to get an x value of 1. All right, and this is going to be what allows us to divide that x-axis again into some intervals that we can take a look at. All right, I'm going to go ahead and put the x value of 1 on the number line, right? This is representing our second derivative, right? And that's going to give us two intervals, right? I'll call this interval A and interval B, right? So interval A is everything from -infinity to +1, and interval B here is everything from 1 to +infinity. And we're going to go through the same exact process, right? We're going to pick a test point in each of those intervals. This time we're going to plug it back into f double prime of x, right? The second derivative. And we want to know, is it positive or negative, right? And that's going to tell us if it's concave up or if it's concave down, right? So let's go ahead and pick, I'll say x equals 0. We'll do interval A, right? We're going to plug it into the second derivative. So I'm plugging it into this function. So we've got 6 times 0 minus 6. That'll give us 0 minus 6, or -6, right? And if the second derivative is less than 0, if it's negative, right, then our function should be concave down on that interval, right? So this will be concave down, which means sad face, right? On this other interval, right, we'll pick a test point. I'm going to do x equals 2 for interval B. We're going to come put the 2 inside of our second derivative, so f double prime of 2. This will give us 6 times 2 minus 6. 12 minus 6 is +6. Right, again, we don't worry about the number per se. We just need to know, is it positive or negative? That means that this is going to be concave up. Right, so anytime your second derivative is greater than 0, it's going to be concave up. So smiley face. Right, and now let's go back and take a look at our graph, and let's look at the components where it's either concave down or concave up, right? And this does change concavity. So since it's going from concave down to concave up, then we can actually answer the question right here while we're on the screen, right? We are going to have a point of inflection at this x value of +1. All right, so let's go take a look at our graph and make sure that matches up with what we're seeing. All right, and so this time I've added in that x value of 1, right? You're going to see that represented by the dashed line in purple this time around on the graph, right? And that's just to separate now those two intervals. I'll turn these other two off from the first derivative, right? So that only that one appears, right? And now we can take a look at what is happening with the second derivative, right? Everything from -infinity to 1 should be concave down, and it is. If I come in here and annotate my graph, right, you'll see that this portion of the graph, right, makes that frowny face, right? So this is where your second derivative is less than 0, right? That would be where it's going to be concave down. And then from 1 to +infinity, right, this is a portion of your graph that is concave up. It makes the smiley face, right? So your second derivative is greater than 0, and that's where your graph is going to be concave up, right? And then we talked about that point of inflection, right, where concavity is changing, in this case from going concave down to concave up. It occurs here at this x value of 1 and that point on our graph. This will be your inflection point. Right, so make sure that, again, the work that you're doing matches up with what you're seeing on the graph. It's kind of a nice way to confirm that your answers are correct, right? And if you find an error somewhere, then, or something doesn't match, go back and see if you can figure out where the error is, either in your work or on your graph if you typed in something incorrectly.